only if, that's spelled IFF, if and only if f prime of c is a real number. Okay? So what does IFF mean? If and only if. If you want to, you can turn this sentence into two sentences. I'll say them both. Whenever you're if and only if, that means the sentence can be worded two different ways. You can say two if-then sentences. Here's the first one. If f is differentiable at the point x equals c, comma, then f prime of c is a real number. You can also switch it around. IFF allows us to switch it around now and say it the other way. If f prime of c is a real number, then f is differentiable at the point x equals c. So what we call that biconditional. And you can say that if then both ways. Okay. All right. The next one is also an IFF statement. F is differentiable on an interval a comma b, if and only if it is differentiable for every value of x on the interval a comma b. So this can be worded as two conditional statements as well. Two if-then sentences. And lastly, if f is a differentiable function, if and only if it is differentiable at every value of x in its domain. So we have differentiable points, differentiable intervals, and differentiable functions. Okay? Okay, so the only one that's even slightly difficult to understand maybe is the last one, but I think you're going to be just fine with it. So let's expound on this last one just a little bit. Okay? F of x equals 1 over x is a differentiable function. But f of x equals absolute value x is not. So I'd like to see if you know why that is. Why am I saying that 1 over x is a differentiable function, but not absolute value of x? So I'll pause the recording now, so you guys can contribute to that. So good answers on that. You're basically going to want to put a because on this. So you could put because the two branches, or just put because each of the two branches, or even just each branch of the hyperbola is smooth. We're going to flesh that out in a few minutes. Smoothness is not the only important thing. Okay? There's another criteria for differentiability, not just smooth, but also we have to have slope. So we'll talk about that in a minute. But the idea is that at least that graph is smooth, and then f of x equals absolute value x is not a differentiable function because there is a sharp turn in the domain. Now, do you suppose there are other functions that have sharp turns in them, or is it just absolute value x? Because all the other graphs on my wall seem to be pretty well behaved, right? They're all smooth. It seems like only absolute value x has that sharp corner kink in it. Is that the case? Is he the only graph in the universe that has that? Okay. So obviously, cities like that are usually no, right? There's probably other graphs, but can you think of any offhand? Yes. Yeah. In fact, absolute value x is a piecewise function. It's y equals x on the right side, and it's y equals negative x on the left side. I tried to convince my pre-calc students yesterday. We were studying piecewise functions, and it's the first time ever seeing it. And they wanted to use absolute value x as one of the pieces. And I was trying to convince them that absolute value x is a piecewise function. So you're sticking a piecewise function into one of the pieces of a piecewise function. Okay, so yeah, you're right. A lot of piecewise functions come together to form these sharp terms, right? You saw some in your homework. so let's go on though. Let's try an activity real quick with our calculators. Let's graph y1 equals absolute value of x plus 2. And let's zoom in several times towards the point 0, 2. Okay? So I'm going to get my calculator ready here. Let's see here. Okay, we're going to do absolute value x. So you probably know where that is. You can find it under math, numbers, the first option there. Or you can go to catalog, it's the first option. So absolute value of x plus 2. And it says to do a zoom standard. So I'm going to do a zoom standard. Notice that this angle right here doesn't really look like it's supposed to. This is supposed to look like a 45-degree angle. Okay? The absolute value graph is supposed to make a 45-degree angle with the x-axis. Something doesn't seem quite right. So notice that that's not a 45-degree angle. Not quite. Does anyone know why? It's 45 degrees, right? Slope is 1. Over 1, up 1. Over 1, up 1. Should make a nice 45, 45, 90 triangle here with the x-axis, or at least the y-axis too. Okay, it's because the piece of plastic that they used when they made the TI-84 calculator, that little piece of plastic, is not a square. It's not a square piece of plastic. So the left side represents negative 10, the right side represents positive 10. And the y is scaled the same way. But the negative 10 to 10 on the x-axis is physically larger. It's a bigger piece of plastic, wide, and very tall. So these don't look like they're sloped quite right. So something you should know about in calculus is most of the graphs you graph, all the graphs you graph, if you just press zoom standard, you're going to see a distorted view of the truth. You would think that these lines were like slope a half or something, or something like that, or slope 3/4, but they're actually slope 1. So what you probably should learn about is the zoom square button. So go down to zoom square now. So we did zoom standard and zoom square. And now you can see this is the truth right here. This thing is not distorted at all. Each x tick mark is the same size as each y tick mark. Okay? How many of you knew about zoom square? Okay. So that looks correct. Now we're going to zoom in towards the point 0, 2. Okay, so zoom in. When you press zoom in on a TI-84, it doesn't actually zoom in. You have to choose where you want it to zoom in. So go ahead and position your little cursor guy near 0, 2 and press enter. And we'll use that as the center of your zooming. Okay, so we zoomed in once. Let's zoom in again. Zoomed in twice. Zoomed in 3 times. See, I should have probably scrolled towards 0, 2 a little bit before that last zoom. Let me redo that last zoom. So zoom in, make sure that cursor's near 0, 2. There we go. It doesn't seem to matter how far I zoom in. It looks like a sharp turn, right? Okay, so this is why we cannot draw a tangent line at a corner. Because no matter how close we get up close to the first one with the curve, but we can't draw the tangent line because we can never decide if we're supposed to use slope -1 or positive 1. You can't use both to draw a tangent line. Tangent line has exactly one slope. So for this reason, we would say that this graph is not differentiable at 0, at x is 0. You just can't draw a tangent line. Okay? All right. So much for that graph. Okay, let's write down what we noticed. So we're just going to write, there is a sharp turn at 0, 2. Okay? And it stays sharp, I guess you could say. As you zoom in, it just looks sharp. It's always sharp. Okay, let's go to the next page on this. Let's switch it up now, and let's graph this function. Okay? let's go ahead and do that zoom, standard, and zoom square again. So zoom option 5 and 6. Okay, that's the old graph. Let's put in a new one. Clear this out. We're going to do square root of x squared plus 0.001 plus 1.99. Graph. Zoom, standard, and zoom square. Well, how about that? Is that the same graph? What do you guys think? Yeah, it looks really similar. The reason it looks similar is because the square root of x squared plus 0.001 plus 1.99 and absolute value of x plus 2 output almost exactly the same numbers. Okay? If you could see the tables side by side for these two, they are pretty much the same. I mean, they're really, really close. Okay? The reason is the absolute value of x squared is absolute value of x. I meant to say the square root of x squared is absolute value of x. Okay? When you simplify the square root of x squared, you're supposed to put absolute value of x. And then here's your plus 2. So I've got this function. It looks very, very similar graphically. Let's repeat our little zooming game where we zoom in towards 0, 2. See what we get. So we zoom in. Make sure we're near 0, 2. Yep, looks like a sharp turn, all right. Let's zoom in again. Hold on here. Wait a minute. I'm not so sure this is a sharp turn after all. You guys see what's going on here? It's looking kind of rounded now. Let's try one more. Okay, I changed my mind. Definitely not a sharp turn at 0, 2. Okay, so what exactly is the difference between these two functions? Now, this particular graph is differentiable at 0. In fact, we could find its derivative. Now, using the long definition of derivative, this would be quite ugly. Reduce conjugates would be quite ugly to do. Okay? The other one, the absolute value of x, you can't take the derivative of that at 0. Like, you really cannot. It's impossible. But this one is possible. You could do it. So graphically, they're quite similar, but you see this one does not have a sharp turn. So technically, it's a totally different family of curve altogether, no matter how similar they look. Okay? So I borrowed that from the book. That's straight out of the Finney DeMonowait's Kennedy book. I just grabbed the little group activity and did it as a demonstration. But it's pretty neat, and it shows us something. So I'm going to put here that y1 equals square root of x squared plus 0.001 plus 1.99 does appear to be differentiable. I'll just write DIFF at x equals 0. Very different conclusion from that absolute value graph. Okay, so take away two things on this. Not every sharp-looking point is a sharp point, and not every sharp point that appears sharp is a sharp point. Not every rounded point is differentiable, and not every sharp point is not differentiable. So you have to kind of zoom in. And once you zoom in far enough, you can see whether you think it is or isn't. Obviously, we don't do zooming. We test the derivative. In reality, we wouldn't just zoom on calculators. We don't trust our eyes. That's why I put it seems differentiable. Okay, now on this one, I'll let you trust your eyes. What you see is what you get. And what you see is what I see. So go ahead now and decide, where do you think this graph is differentiable or smooth? Okay? And where do you think it is continuous but not differentiable? And where do you think it is not continuous and not differentiable? Okay? So it's 3 different questions with 3 different interval answers. So I'll pause the recording while you work on that. Right, good job. So we have negative infinity all the way up to -1, but not including that sharp turn there. And then from 1 to 3, and then from 3 to 4. Do you guys remember what this symbol means from pre-calc? It's the union symbol. Technically, it means or, because you cannot position your finger or your pencil in more than one region at a time. So you pick either this region or it's this region or it's this region. So we use the or symbol for that. But the other way you can interpret the U is imagine putting all this together into one meaningful list. These are all the points. This set is made up of 3 smaller sets. So this set of differential points is composed of this, all united. Somebody used the word and, but it's actually differentiable. But anyway, continuous but not differentiable. That's a little bit easier to do. So yeah, let's talk about the end bracket here. Some people would put a rounded one, some people would put a square one. Okay? I'm not going to be too picky on it. The AP test in its 55 years of testing has never once asked about differentiability at an endpoint. No, I can see. So, and I've seen great teachers on both sides of that argument. Like, people can't agree on it. So we're not going to fight about it, and we're just going to let you put whatever you want there. Okay? That's a good question. Is there a derivative at x equals 4 or not? There's a left-hand derivative. There certainly is no right-hand derivative. There's no function of it. If it's good enough to have a closed point and what looks like a horizontal tangent right there, if that's good enough for differentiability, then I suppose we could include it. Okay? Don't stress too much about the endpoint. What about continuous but not differentiable, part B? So this only happens at x equals 1. There are other not differentiable places, but they're at places where the graph is not continuous. So not continuous and not differentiable. Does anyone know why that's kind of a silly question? Why is that kind of a silly question? Yes. Correct. If it isn't continuous, there's no way it can be differentiable. So this part of the sentence is literally redundant. Of course it's not differentiable. I just said it's not continuous. How can a roller coaster be smooth if there's a piece of track missing? If they take out a section of the track, you'll probably die, right? But if you take out a section of the track, there's no way to say it's a smooth ride. I don't care, how you describe it. You can't use the word smooth. Okay. All right, so not continuous is really all this means. But be careful with your answer here. So the curve is not continuous at x equals 3 because we have to lift our pen as we pass through that point. The limit exists, but f of 3 is undefined, right? And x is greater than 4 would be a description of the rest of the points where the graph doesn't continue on. Okay? So when you list points of discontinuity, you need to include points that are outside the domain. Okay? All right. Let's go to the next slide. Okay, there are 4 ways a function can be non-differentiable at a point. Okay? One of them is the corner. We just saw that with the absolute value curve. Sharp turn right there. Okay? So maybe the slope on the left, you're drawing tangent lines, the slope on the left is just -1 consistently, or maybe it's approaching -1 or something. And the slopes on the right, these tangent lines, they all have slope 1, or maybe they're approaching 1 as you come in towards x equals c. But you do have this abrupt change in slope between one number and another, maybe -1 and 1. Okay? So at x equals c, handwriting's pretty sloppy with the stylus. At x equals c, the slope abruptly changes from a negative to a positive. Or even from a positive to a positive. Like you could actually have a situation like this. The graph is rising, rising, rising. And then now it's rising, 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 but it's a different slope. Or you could have a curved version of that. Rising, rising, rising. It's about to reach slope 1/2. and now it's rising, 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 but the transition is just too sudden. And the slopes on this side are approaching a half, and the slopes on this side are approaching 3/4 as you come in towards C or something. So the very last tangent line, I guess you could say, is a half, and the very first tangent line is 3/4. And that's a sharp jump. See? Okay. So that one's kind of obvious. Here's another one. We could have a curve that does this. Okay? And if this happens, the slopes on the left are getting more and more negative. More and more negative, more and more negative. In fact, right here, we can see that these slopes are getting to be like -10, -100, -1,000, and the slopes are basically going to -infinity as you approach x equals c here. And then on the right side, all the slopes are positive. And as you come towards x equals c, those slopes are more approaching positive infinity. So you can have this situation as well, and this would also be considered a sharp turn. In fact, it's razor sharp, okay? And the slopes are opposite infinities. Okay, the first one's called a corner, the second one's called a cusp. Corner, cusp. Okay? The third one is one that's a little bit surprising. It's this one. Now, this one is very different from the other two. On the other two, if you zoom in on your graphing calculator at x equals c, you'll find that that is just a plain sharp. The point is a sharp turn. And you can try to sketch a tangent line there, but it won't work. On this curve, this is different. If this was a roller coaster, right, and you were going along the track, you would pass right through this point at x equals c. Let me label my x equals c here. You would pass right through this point at x equals c, and you wouldn't feel a jolt because the track is perfectly smooth. But at that instant, you would have vert, as skateboarders like to say. That ramp's got vert, or I got vert. That means your skateboard hit a section of a ramp that was truly vertical. It's a neat feeling. It's weightless. Okay? And that section of this curve has vert. Verticality. That's a word. So, right there, we can draw a tangent line, but we cannot say that the curve is differentiable. Why? Maybe you thought not differentiable means you have to have a sharp turn. This does not have a sharp turn, but there's something wrong with the slope. The slope is what? Good, undefined. So this is the third case and sort of the one that's sort of subtle. They love to test on this one, okay? On this graph, there is a tangent line at C, but it doesn't have a slope. It doesn't have a meaningful slope. So this is another way we can have non-differentiability. This is called the vertical tangent. This year we'll just call it a VT. It's an extremely important thing on the AP test. Let's go back to our first slide today, okay? What does the first sentence say? It will be differentiable at C if what? The slope is a real number. Doesn't say it's differentiable if you can draw a tangent line. It's differentiable if you can draw a tangent line, and that slope is a real number. Infinity is not a number. Okay? That's an idea. Okay, let's go to this last one. Last one's the easiest one. Anytime the graph breaks, whether it's a point discontinuity or a jump discontinuity or an essential discontinuity, any kind of discontinuity, whether it's the red, the blue, or the green, we would say that it is not differentiable. Okay, so let's just call this x equals c. Right there. That's x equals c. If the graph jumps, or there's even just a tiny hole, or there's an asymptote, then that's the fourth reason why we would say a graph is non-differentiable. So discontinuities. Okay. All right. Let's go to the next slide. I have here 4 graphs, and I would like to study them to see if I think they contain corners, cusps, vertical tangents, or discontinuity at x equals 0. Okay? But before you grab your graphing calculator and go type them in, I think you should know every one of these graphs from memory. Okay? So we're going to try to learn how to look at the graphing calculator. Let's see if we can sketch secant x and tan x plus 1. So for secant x, we're only going to be graphing between negative pi over 2 and 0. So just this small region here, and hopefully you remember what secant looks like. You can use a cosine graph to figure it out. If you have to peek on the wall, you can peek on the wall. Okay, so we're not drawing much of it. We're just drawing this piece here. Okay? And tangent x shifted up a space. Tangent x shifted up a space. So many of you remember the tangent graph because it's the first graph we ever drew that has an infinite number of discontinuities in it. Oh, I forgot to shift them up a space. Those are tan x branches. Let's move them up a space. I'm just trying to miss that last one. The first one, the fundamental one. Okay, so this one should come up like that. There we go. Okay, question for you. Is that thing smooth at 0? Right where the two come together, red and blue makes purple right there, right? Yeah, okay, so what's going on at x equals 0? Is it smooth or not? What do you guys think? It looks smooth. It looks smooth because I drew it wrong. Look very closely at the tangent graph. The tangent graph has a slope of 1 at the origin. It has a slope of 1 at the origin. It's actually tilted. The graph of secant is completely flat at the origin. So this red part is approaching a slope of 0, and it's about ready to go back up again. Right? So the red thing, if you keep drawing, it go back up again. This graph is coming from underneath and cutting up through, and when it hits x equals 0, 1, or x, y equals 0, 1, it comes out of that point 0, 1 at a 45-degree angle to the x-axis. So if you could zoom in on that point right there, okay, you zoomed in, you can see what I'm talking about. It looks like this. Here's your y-axis. Okay, here's the point 0, 1. The left side's coming in like this, perfectly flat. The right side's coming out like this. Not the same slope. Now, how do I know that? Well, do you guys remember in the last chapter I had you do this limit for me? You guys remember this limit, right? This is 1, right? Do you remember when we did it with a tangent? I'm sure we've done it with a tangent too, right? Didn't this come out to be 1 also? Think about what this means, folks. If tan x over x is 1, right? That means tan x and x are the same graph. Now, it's only true near 0, but when you are very, 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 very close to 0, it is impossible to tell a difference between tan x and y equals x. Okay? So tan x and y equals x. Tan x looks like this at the origin. X looks like this as the origin. And if you're zooming in real close, you cannot tell the difference. That's why their ratio is 1 when you're near the origin. And what's the slope of y equals x? Always and forever. 1. So what's the slope of tan x when you're near the origin? 1. Yes, not 0. Not like the secant graph, right? Okay, so hopefully that more or less convinces you that that is a, what, cusp, corner, vertical tangent. What is that thing? The slope on the left is approaching 0. The slope on the right is approaching 1. That's a corner. 2 different numbers. Okay? Okay, so this is a corner. And you could have graphed it on the calculator in 2 seconds and answered the question, right? All right, let's look at x to the 1/3. X to the 1/3. You might say, I do not know that graph. You're going to make me draw a table. Okay, but remember, x to the 1/3 has an inverse function, y equals x cubed. Inverse is a big part of this chapter, and we haven't done it yet this year. Listen, if you can graph y equals x cubed, then you can graph y equals cube root x. Because they are related through a simple reflection. Remember that if you can graph y equals x cubed, and then reflect it over the y equals x line, that is the graph of y equals cube root x. So let's do that real quick. We all know how to graph x cubed. If you don't, you're definitely not in the right class. There's x cubed. And simply draw the y equals x line. Okay? And reflect the x cubed curve over the green line. This is y equals cube root of x, or you could say x to the 1/3. So you actually know twice as many graphs as you think. For every graph you know, there's an inverse graph. So you know x cubed, you know cube root of x. So you don't need a calculator for every little thing. Okay, so that's our graph. How would you describe what's going on at the origin? I asked you to classify the type of non-differentiable point. So the origin is definitely a non-differentiable point. Look at the 4 different kinds we have. Yeah, this is a vertical tangent case. You're right, this is a vertical tangent case. So vertical tangent. I said I would write VT. Oops, forgot. So VT. Good. Okay, what about x to the 2/3? X to the 2/3. Before you get your calculator out or before you make a table, think of x to the 2/3 as x to the 1/3 that has been squared. What would happen to our graph of part B if we squared it? So I've got the graph of x to the 1/3, and now I want to square that. What's that? Okay. Maybe, yeah, we would probably expect something fishy to happen at the origin. So, listen, the outputs of this function that we just drew are both negative and positive. going to reflect up in a very similar way to when we do an absolute value. But its value will also increase because we're squaring it. So squaring is one of those functions that forces it to look even. So it's going to create a y-axis symmetry. This thing's probably going to be a lot steeper because we're squaring. But it's going to look like a seagull. In fact, I call these seagull graphs. Looks like this. Probably a little steeper actually on the sides. But do you recognize this scenario? Is that a corner or a cusp? What is that thing? This is a cusp. Right. And the next one's pretty easy because you know the graph. And calculus is always easy when you know the graph. This one goes like this. And at the origin, it's not even continuous. So naturally, it's not differentiable either. So we would just call this a discontinuity. Okay, so as you guys leave, I'm going to finish up recording a couple more slides. And your job this weekend is to watch the rest of this video, okay? There's a little bit of technology there that I want to go over. How does a calculator find a derivative? How do you graph a derivative on your calculator? Come in Monday with those watched, and you'll be comfortable working in class with next assignment, okay? Okay, on our next slide, we're trying to show that this function is not differentiable at x equals 0. Now, show that and describe a graph, those are two different levels of amount of work, you know. So, I mean, you can certainly graph this. It's just the y equals 0 line when we're on this side of the y-axis, and it's the y equals 1 line when we're on the other side, or including y equals 0. So, I mean, including x equals 0. My point is, you can easily tell it's not continuous. So how would you then show that it's not differentiable? So what you do is you'd show that the left-hand derivative is not the same as the right-hand derivative. So we just do limo left, f of 0 plus h minus f of 0 all over h. And we'll do limo right, f of 0 plus h minus f of 0 all over h. We'll just try to show that these are not the same. Okay? All right. So, let's go to the first one. So if we rewrite the blue one without the superscript, then it means we're committed now to picking the very left piece. So the left piece is what we'll use for 0 plus h. Remember that in this case, h is some small number. So if this is x equals 0, 0 plus h is actually to the left of it, because we're approaching h goes to 0 from the left. So you can think of h as negative 0.001, for example. So we're actually physically on the left piece, and that's why we have to pick the left function, which is 0. Minus, and then f of 0. For f of 0, we have no choice but to pick 1. If you look at the original graph, f of 0 is clearly 1. Okay, this leads us to the limit, negative 1 over h, or we could pull the negative out. And this is like studying x equals 0 region of the 1 over x graph. It's clearly a does not exist situation. Right? Okay, so it doesn't really matter what the other side turns out to equal. It's not going to be the same. So, since we were coming from the, actually, let's not call it D and E. We'll give it an actual infinity type answer real quick here. So it's 1 over h. We're coming at h from the negative small numbers. So h is 0.01. So it's like negative 1 over negative 0.01, negative 1 over negative 0.001, so on. So this is going basically to infinity. We'll just write infinity so it does not exist. The limit technically is non-numerical, but we'll say infinity. So what's going on there is, look at these purple lines. You're connecting a point on this side to this red point up here, see? And the closer you get, as you move your h inwards this way, the steeper that line gets until it's pretty much vertical. So that's why we're getting m equals, m is going to infinity here. M is going to infinity. go and look at the red part. The red part's pretty obvious. You're using limo, and we're going f of 0 plus h. Now h is like 0.001, so it's a positive number. So 0 is here, 0 plus h is to the right of that. Okay, so we'll use the first piece, which has a y coordinate 1, minus f of 0. F of 0 is 1, as defined, over h. And this gives us limo, I guess limo plus 0 over h. This is just 0. And infinity, last I checked, does not equal 0. Right? Okay, so this proves that these are not the same. All right, now let's go on to our next slide. How does a calculator find a derivative? Okay, so the first thing you need to know is that a calculator does not actually understand derivative rules. Okay, a calculator does not understand derivative rules. It merely approximates. Okay, it approximates. It actually uses average rate of change, not instantaneous rate of change. Also, it can only find the derivative at a point. There are a few calculators with a CAS chip, computer algebraic system, and those can actually find derivatives as expressions. As you know, the T99, if you type what's the derivative of x squared, it actually says 2x. And most calculators can't do that. We're going to use the calculator to find the numerical derivative. That just means it uses AROC as an approximation of IROC. At x equals 2 for the function 2x cubed plus x squared minus 1. Okay, so I'm going to do that real quick. If you just turn on your calculator, just go to the home screen. And you could just press Math 8. Math 8 will give you this, or maybe an older notation if you have the older operating system that looks like this. Inderiv. Okay, in any case, you're going to type the function, okay, in this space right here. Okay, so our function is 2x cubed plus x squared minus 1. And we're interested in deriving or taking the derivative with x as our independent variable. So we're going to put an x right here down under the d dx. Okay? All right. And then scrolling over, one last little thing, we have to tell it where we want to find the derivative. We're going to find the derivative at 2. So this is going to find the slope of the curve 2x cubed plus x squared minus 1 at the point where x is 2. Okay, now if you have the older operating system, you have to type 2x cubed plus x squared minus 1, comma x, comma 2. That's how we type that. Okay? All right. When you press enter, it will give you the result. 28. 28. Okay. Notice it's not exactly 28, but f prime of 2 is approximately 28. The reality is that it is exactly 28. The calculator's having trouble knowing that it's exactly 28. Okay, what if you don't have a calculator? Well, you could still do this, or I should say, what if you don't have a calculator with a numerical derivative feature? You can still use this thing, which is called the symmetric difference quotient definition of a derivative. Okay, it's a little different from the limo x goes to 0, h goes to 0, you know, f of x plus h minus f of x all over h. It's also a little different from f of x minus f of a all over x minus a, so where the limit goes from x to a. Those were two previous definitions. This is kind of a third definition of derivative. Okay, and we can actually just use it pretty much on any calculator to come up with a derivative. So here's how it works. Pick a really small value for h, say 0.001. Okay, what you do is you would go like this. You would assume that a here is 3. So a is always your at value. Sorry, a. If you see at x equals 3, that's your a. So you're going to be doing f of 3 plus 0.001 minus f of 3 minus 0.001 all over 2 times 0.001. Okay? In other words, we're going to find f of 3.001 minus f of 2.999 all over 0.002. Okay, so here's what's going on. The curve at x equals 3, it's up here at like 19 or something, okay? So I don't know. I don't know if it's a maximum or whatever. We could graph if we wanted to and spend some time on it, but that's not the point. We're just trying to study x equals 3. So what we're doing is we're finding the slope between 2.999 and 3.001. Okay, the rise here is 3.001 minus 2.999. The run is 0.002, or 2 times h. Okay, so we really are just doing an average rate of change here. But because it's such a tiny little window, we believe the slope of this purple secant line is extremely similar to the slope of the green tangent line here. That's the basic idea. Okay, or just memorize the formula. Okay, so it's basically going to all get plugged in. We have 2 times 3.001 cubed plus 3.001 squared minus 1 minus 2 times 2.999 cubed plus 2.999 squared minus 1 all over 0.002. And when you run this, you'll need a calculator probably also, but it could be even a little basic 4-function scientific calculator even, or even just a calculator with no science features, like one of those ones you use when you're 3 years old. You never used one at 3. But let's try it out. So we're going to do 2 times 3.001 to the third, and then plus 3.001 squared, and then minus 1. And let's put that in parentheses. Okay, so that's all in parentheses. Minus, probably didn't need that parentheses now that I think about it. For this next part we will. Minus 2 times 2.999 cubed plus 2.999 squared minus 1. And that gives us this. And if we divide that by 0.002, Mr. Shore must have made an error here somewhere. 2.3001 cubed. I'm just going to scroll back through this again. Plus 3.001 squared minus 1 minus 2 times 2.999 cubed plus 2.999 squared minus 1, and then divided by 0.002. Make sure that's right. So our answer that we're getting here is 60. 60, yeah. And now let's go back and use the inderiv thing. So let's go and try the actual built-in program for that. So let's go to Math 8. We'll take the derivative with respect to x for 2x to the third plus x squared minus 1 when x is near 3. And the answer is 60. In fact, if you look at it closely, it's 60.0000002, which seems to be fairly strong evidence that the calculator is using the symmetric difference quotient when it calculates a numerical system. Okay, so this does leave us with a little bit of frustration. We can find things like f prime of 3 is 60, but it doesn't seem like we can just find the derivative in general from a calculator unless we have a CAS-enabled calculator. Okay, one thing we can do, though, with just about any graphing calculator is to graph the derivative of a function. Okay? So let me show you how you can do that real quick. We're going to graph x equals 2/3 and its derivative on the same screen. Okay? All right, so let's try that. So we're going to go to the y equals screen, and we're going to type x to the power 2/3. I'm just going to clear this out. X to the power 2/3. Okay? And then down on y2, we're going to press Math 8 ddx of, and now you can type x to the 2/3 again, or just press variables, y variables, function y1. And then, because we don't want to see the graph of the derivative at any particular x, but rather we want to see the graph of the derivative at all x's, we would go ahead and put an x here. Now this is going to fool the calculator into plugging in an x, say 0, and then it will find the numerical derivative and plot that point. Then it will plug in 0.001, and it will do it again. And it will plot 0.002 for your x, and it will find the derivative there. And it will plot the derivative slowly, and it can be quite slow. We're going to see two graphs here in a minute. So if you want to, you can turn off the first one and only look at the second. Or if you want to see them side by side, one thing you can do is scroll over here and change this thing right here to some other symbol. So put your cursor on it and press enter a couple times. Here's one that will make it thick. I just pressed it once. So the graph of the derivative will be thicker looking than the graph of the function. So here comes, oops, let's do zoom standard and a zoom square. Zoom standard. I want to do zoom square too, so I'll press on to abort that, and then I'll press zoom square. Okay, it's going to look real nice, and it'll be squared and not distorted. There's that seagull graph we talked about a couple slides back. Here comes the derivative graph. It's thicker, and it's graphing slowly. Remember what it's trying to do. It's trying to calculate the derivative at many, many values of x, and then slowly plot them out. Kind of wish we zoomed in. Okay? In fact, I'm going to. So I'll zoom in one time. I'll pause the video so you don't have to watch it, and then I'll put it on when it's ready. All right, that took a good 30 seconds that you didn't have to waste. There is your graph. Almost looks like the 1 over x graph is our derivative. But if you remember how to find a derivative, that's not actually quite right. Okay, so there it is. Pretty neat. One last little warning about your calculator. Okay? Let's see here. I'll show you something real quick. If you ask the calculator to find the numerical derivative of the absolute value of x at 0, watch what happens. Okay, so we'll go to the home screen, quit. Okay, we'll press math 8, do a derivative with respect to x. We'll type absolute value x here, and we'll type x equals 0 here. Detach the screen. You can see better. We know darn well that this is not supposed to give us an answer. Remember, the graph of absolute value x isn't differentiable at 0. So we would expect the calculator to say, oh, there's no such answer, or error, or something, right? But watch what happens. 0. The calculator thinks the derivative is 0. It thinks there's a slope, tangent line with slope 0 at the origin. That is not the case. What is going on? So it's because the calculator uses that symmetric difference quotient. See, here's the graph of absolute value x, right? And the calculator is literally choosing a point on each side of x equals 0, right? It's choosing a point on the left side. Bring it back up. It's choosing a point over here, maybe at negative 0.001, and then one point over here at x equals positive 0.001, and it's calculating the average rate of change between them. So it's literally calculating this slope, see? And it thinks the slope is 0. So we have to be very careful. Sometimes our calculator doesn't handle non-differentiable points very well. And so if you're asked, hey, what's going on, you know, at the origin for a particular graph, maybe you're back on these problems here doing remember when we were doing these? Right here. Hold on. Right here. When we're doing these ones, or these ones, the calculator won't really help you that much. I mean, looking at the graph helps, but you can't just say, hey, what's the derivative of 0? It's not going to say undefined or whatever. It's going to actually try and give you a number, okay? Look at this vertical tangent one, x to the 1/3. Let's see what the calculator does with that. I'm actually not sure, so we're just kind of playing around. By the way, if you don't want to retype something, just press second, enter, and it will kind of resurrect what you typed earlier. Okay, so it goes through your history. X to the 2/3. Let's see what it does with this one. See, it thinks that derivative is 0. That doesn't even make sense. If you look at the graph of x to the 2/3, how could the derivative be 0 for this seagull graph here? Oh, I see. It's doing that same thing again. It's measuring across from one point to another. Let's try x to the 1/3 is what I meant to type. That's what, sorry. So x to the 1/3, and let's turn off the derivative graph. We don't need that. See, look, this is the graph. The slope is infinite at the origin. Let's see what the calculator does with that. So, second entry. Let's change this to x to the 1/3. 100. It thinks the slope's 100. It's actually infinity. So, it's undefined. But anyway,